Alright, AP Stat students, welcome to Chapter 6. This is going to be a really important chapter on discrete and continuous random variables. It's still very probability based, but we're going to start learning some things that we're going to be using throughout the rest of the school year. So a random variable takes numerical values that describe the outcomes of some chance process. The probability distribution of a random variable gives its possible values and their probabilities. We have two main types of random variables, and that's discrete and continuous. We're not really going to use anything else in this class. Think of flipping 3 coins. What are the possible outcomes? So we can draw a tree diagram to illustrate this. So we have our first flip, where we get a heads or a tails. Then we have our second flip, where we also get a heads or a tails. Then we have our third flip. So what we have is we have a heads, 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 tails, heads, tails, heads, heads, tails, 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 heads, heads, tails, heads, tails, 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 heads, and tails, tails, tails. How could we assign numerical values to describe these outcomes? Well, what we could do is we can make this probability distribution, because a numerical value is not going to be heads, tails, but we could count the number of heads. So we could say 0 heads, 1 head, 2 heads, 3 heads. So let's make x the number of heads. So we could have 0, 1, 2, or 3. What's the probability that we get 0 heads? Well, that only happens in one branch, that tails, tails, tails. So this could happen one time out of, well, we have 1, 2, 3, 4, 5, 6, 7, 8 different ways that could happen. For one head, we could do that one way, 2 ways, 3 ways, 3 out of 8. I'm going to go to 3 heads because I think that will be the easiest way, because there's only one way to do 3 heads. And then what's remaining goes in here. So there's 3 ways we could get 2 heads. Sometimes it's easier to list them out, and that could help, but the tree diagram helps make sure that you get all of them. We can make a histogram of these outcomes. So there we go. We could see that it's very symmetric, and the middle's about 1.5. In 1952, Dr. Virginia Apgar suggested 5 criteria for measuring a baby's health at birth: skin color, heart rate, muscle tone, breathing, and response when stimulated. She developed a 0-1-2 scale to rate a newborn on each of the 5 criteria. A baby's Apgar score is the sum of the ratings on each of the 5 scales, which gives a whole number from 0 to 10. APGAR scores are still used today to evaluate the health of newborns. What APGAR scores are typical? To find out, researchers recorded the APGAR scores of over 2 million newborn babies in a single year. Imagine selecting one of those newborn babies at random. That's our chance process. To find the random variable x equals the APGAR score of a randomly selected baby 1 minute after birth. The table below gives the probability distribution for x. So this 0 score is this baby that's not going to be doing well, and this 10 is a baby that's going to be doing very, very well. So looking at these probabilities, it looks like they're very low, very low, very low, starting to climb, and then this 0.3, 0.4, it looks like most of these scores are between 8 and 9. So why is this a discrete random variable? Well, that's because we have these values 0, 1, 2, 3, 4, 5. It's not continuous. We have discrete values. Why is this a legitimate probability distribution? Well, all the probabilities are between 0 and 1. And 2, the sum of all the probabilities add up to 1. Now we would have to check this, add this, plus this, plus this, plus this, plus this, plus all of these, add them all up, it'll give you 1. I'm just going to tell you it works, save some time. Make a histogram of the distribution. Describe shape, center, spread, what you see. So, I'm going to use a calculator to do this because I don't feel like drawing it all out, but it would be pretty easy to draw. Now that I have all my numbers in my spreadsheet, I'm going to add a data and statistics page. This is going to be a little different. We're going to add a variable. Alright, so this isn't going to work. For some reason the iPad app is different and I just searched everywhere and can't find what I'm looking for. But this is going to give us the idea. You could see that the probabilities start off small, they get much higher at 7, 8, and 9, and then drop back down at 10. So you can see the majority of these scores are here. On the handhelds, I'll show you how you can use a frequency. You'll insert an X variable with a frequency, and that will help us get there. But for now, we're not going to worry about that. So things to note, the shape is going to be skewed left. The center is going to be around 8. The spread is going to be from 0 to 10. Doctors have decided that an APGAR score of 7 or higher means that the baby is healthy. What is the probability that a randomly selected newborn baby is healthy? So we need the probabilities of X being greater than or equal to 7. You may also write it as the probability of X being greater than 6. In discrete random variables, it's very important that you remember these notations. In continuous, it's not going to matter so much. So this is just the probability that of 7, 8, 9, and 10. So 0.099 plus 0.319 plus 0.437 plus 0.053. So 0.907. So it's about a 91% chance that a baby is healthy. On an American roulette wheel, there are 38 slots, numbered 1 through 36. Plus, there's a 0 and a double 0, so there's 38, again, 1 through 36, 0 and double 0. Half of the slots from 1 to 36 are red, and the other half are black. Both the 0 and the double zeros are green. Suppose that a player places a simple $1 bet on red. If the ball lands on a red slot, the player gets the original dollar back, plus an additional dollar for winning the bet. If the ball lands on a different colored slot, the player loses the dollar bet to the casino. Let's define the random variable X as the net gain from a single dollar bet on red. The possible values of X are 1 and negative 1. So they'll get a dollar if it lands on red. They'll lose that dollar if it lands on black or green. What are the corresponding probabilities? Well, the chance that the ball lands on a red slot is 18 out of 38. And the chance that it lands on a different colored slot is the 20 out of 38, right? The other 18 black and then the 2 green. So here's the probability distribution. There's a slightly larger chance that we're going to lose. What's the player's average gain? Well, what this means, this has a probability of 20 out of 38, and this has a probability of 18 out of 38. So all we're going to do is multiply. That negative 1 is going to be multiplied by this probability. That's the likelihood it would happen. Plus, we have $1 times the 18 out of 38. So this gave us a negative 0.05. So on average, you're going to lose 5 cents-ish, I rounded, every time you spin this wheel. That would be after you play this game a lot. That's how averages work. But if you think about in that long run, you're going to lose a little bit more than you win. So you're technically losing 0.05 if you were to play this game a lot. Why can't we just average negative 1 and 1? Well, the probabilities are not the same. If it was equally likely, we could average negative 1 and 1 and average gain would be 0, but it's not because remember you lose a little bit more. So what did we really do is we just multiplied the value times the probability. So what we're doing is we're multiplying the value x1 times the probability because that's how often it'll occur, plus x2 times the probability, x3 times the probability until we run out. So this is the sum of us multiplying these two values and probabilities together. So this is called the mean, which we also call the expected value. So this is the mean, mu of x. It's a little hard to read. It's a mu of the random variable x. Or that ex is the mean's expected value of the random variable x. So remember the APGAR scores. We define the random variable x to be the APGAR score of a randomly selected baby. The table below gives the probability distribution for x once again. So if we want to compute the mean, or that expected value, the mu of x, or we can call it the expected value of x, remember that's the same thing, we just multiply. So 0 times 0.001 plus 1 times 0.006 plus 2 times 0.007 plus, and we keep going until we do 10 times 0.053. Now luckily, I already did this on my calculator. So remember we had these in our table, and then we're going to add a calculator page, and we can go to menu, statistics, stat calculations, one variable statistics, and this is where we input our value with our frequency list with the corresponding probabilities. So there, that mean x bar is what we're looking for, right? Because we're looking for the average. So 8.128. Now that makes sense because that's the center of our data. Remember how we said our centers in between 7 and 9? We said around 8. This is the exact center or balancing point of our distribution. So if we want to interpret this mean, we could say the average APGAR score of a randomly selected baby is about 8.128. Interpreting the standard deviation. Well, we've done some interpreting standard deviation before. We could say, on average, APGAR scores differ from the mean by about, or you could say approximately, but we use our standard deviation. Now we can't use our sample because this is everything. This is the population. So we want to use our sigma x, that population of 1.44, which makes sense. The middle was about 8, and on average, it varied by about 1.44. Now remember, because there was the low numbers, that 1 didn't have very much probability and the 0 didn't have very much probability, this is being skewed a little bit by that, but not too bad. Continuous random variables. Imagine I used a number generator to pick 1,000,000 numbers between 0 and 1. So what would you expect a dot plot of the distribution to look like? So remember that if we had a number between 0 and 1, there's infinitely many numbers between those two. So every time I would pick a number, even though I do this 1,000,000 times, I would probably never pick the same number. So a histogram is going to look like a perfect rectangle. So now let's say I pick one random number between 0 and 1. What's the probability that it is between 0.3 and 0.7? Well, here's 0.3 and here's 0.7. Well, there's 40%, right? 0.7 minus 3. This is 40% of that whole 100%. Probability between 0.3 and 0.7 is 0.4. So this is an example of a continuous random variable. There are no gaps between possible values of x. To find these probabilities, we find the area under the curve. Sounds like calculus, doesn't it, for you calculus people? But we're not doing any calculus in this class, but that's where it came from. So many normal distributions are continuous random variables when tied to a chance process. The heights of young women closely follow the normal distribution with a mean mu of 64 inches and a standard deviation sigma of 2.7 inches. This is a distribution for a large set of data. Now choose one young woman at random. That's your chance process. So call her height y. If we repeat the random choice very many times, the distribution of values of y is the same normal distribution that describes the heights of all young women. Find the probability that the chosen woman is between 68 and 70 inches tall. So remember from chapter 2, we have our normal distribution. Okay, it doesn't have to be perfect. With our mu of these y's at 64. And our standard deviation of the y's as 2.7. We want to know the probability that the chosen woman is between 68 and 70 inches tall. So 68, y is in between that, and 70. And we can go to our calculator to do this. Menu, statistics, distributions, normal CDF from 68 to 70. Our mu was 64, and our standard deviation was 2.7. So 0.056. Now I didn't do a good job of drawing this on the picture, but between 68 and 70. So hints for random variables and probability. You need to define the variable. So x was the APGAR score of a randomly selected baby. Y was the height of a randomly chosen woman. We state the probabilities you are trying to find, and you're going to draw a picture if necessary. So if you're using a normal distribution, you're going to draw a picture. So remember, this was x greater than or equal to 7, and the other one was between 68 and 70. Now, because this was a continuous random variable, the symbols don't matter so much. If using a distribution in the calculator, right now you are using a normal distribution, which we did, we'll learn others, that will change. Make sure you state the distribution and parameters. So this is a normal distribution. Since I drew a picture and I labeled my mean and my standard deviation, that's enough. You have implied a normal distribution, so that's great. So we have our distribution, our parameters, mu and sigma. We have our probability statement and our probability. The only thing we should do after that is interpret the probability. We would say in the long run, there's a 5.6% chance that we would randomly choose a woman between 68 and 70 inches tall. So, rule of thumb, if your calculator needs to know the information, it's important enough that you need to state it. Okay, your calculator needed to know that it was a normal distribution, you needed to know the parameters, and you needed to know the probability statement. So make sure you list all of that.